pH. Like the subtitle says here, it's all about making small numbers usable. But we got to kind of cover some bases before we get to that. All right, first we need to talk about self-ionization of water. Remember we said earlier that water can act like an acid and a base, which makes it amphoteric, is what we call that. Because water can act like an acid, a proton donor, and then a base, a proton acceptor, it can in fact actually react with itself, where this water donates a proton and becomes hydroxide, and this water accepts a proton and becomes hydronium. This is called self-ionization of water because water is reacting with itself to form ions. Now, the concentration of the hydronium hydroxide ions will change depending upon how basic or acidic your solution is. However, the product of them will always be the same in an aqueous solution. It will always be 1 times 10 to the negative 14. So if you take one of these, we can always calculate the other. And so in an aqueous solution, they're always going to be related to each other that way. There are some calculations in your workbook on how to do this, but basically plug and chug. You plug in this value if that's what you're given, divide, define this, and so on. It's pretty easy to go back and forth between the two. The problem is that these values are going to be crazy numbers. Okay, that you're going to have like 7.36 times 10 to the negative 9 molar solution, or 3.5 times 10 to the negative 6. Like, dealing with numbers like that is really annoying, and it's really hard to tell how big or small they are. So scientists came up with pH. So it was just horrible trying to use scientific notation, so they used what we call pH. Now, pH is defined as the negative log of the hydronium concentration, or the hydrogen concentration. So when you put P in front of something in chemistry, that means you're taking the negative log of it. There is such a thing as pKa. We're taking the negative log of the Ka values we saw in the last lesson. pKb, you're taking the negative log of the Kb value we saw in the last lesson. There's pOH, where we're doing the negative log of the hydroxide concentration. So P just means negative log. That's what it means. And then whatever's behind is what you're taking the negative log of, in this case, hydronium. So because of the ionization constant of water being 1 times 10 to the negative 14, the values for hydronium and hydroxide can be anywhere from 0 to 1 times 10 to the negative 14. And when you take the negative log of that, that gives you values between 0 and 14. And so we get this. And so we get a pH scale. And so 0 being the strongest acid, 14 being the strongest base, and then 17 is down the middle, and we call that neutral. So as we move down, we get less acidic until we get to neutral, and then we start getting more basic as we go this way. You kind of see some general ideas here. Now, one of the important things to understand about this is a logarithmic scale. It is based on logs. You don't have to go back and do this horrible remembering how logs work. You just need to know how to use the log button on your calculator. But what a log means scale. So if you remember, this is log base 10. You know, if you remember back from your algebra days way back when. So this is log base 10. And because it is base 10, every time I change a number, I'm changing by 10. So for example, going from black coffee to lemon juice, it's not 3 times stronger. It's 10 times, 100 times, 1,000 times stronger. Because every time you go, you're going by tens, or multiplying by 10. And so this has 1,000 times more hydronium ions than coffee does. And it's considered to be 1,000 times more in that sense. Stronger may not be quite the right term there, but you get the idea. And so that's pH. So as I mentioned earlier, there are other P things, and so there's pOH, which is the concentration of hydroxide ions. And it's done exactly the same way, negative log of hydroxide. So it's the opposite of pOH. I mean, pH and pOH are opposite of each other. So a pOH of 5 is equivalent to a pH of 9 because they're always going to add up to give you 14. And so we can interchange between them pretty easily. One of the other things you'll run into is sometimes, so pH is helpful for us in terms of just everyday life of, hey, let me use numbers that I can really think of and use. So like what we were using here. Numbers between 0 and 14 are a lot easier to use and a lot easier to think about. And they're a lot easier to talk about. But those aren't the actual concentrations. And so I need some way of going back from pH to those concentrations. Because it's the concentrations that allow me to do the chemistry math that I need to do. And so the opposite of a log is exponential. So hydronium would be 10 to the negative pH power. These are exponents up here. It's a little bit harder to see, but these are smaller. These are exponents. So 10 to the negative pH. So if you had a pH of 9, you would find the hydronium concentration by doing 10 to the negative 9. Then the hydroxide concentration would be 10 to the negative pOH, whatever it happened to be. And so we can use pH and pOH to go back to figure out the concentrations. So let's look at a couple examples here. So let's determine the pH and pOH for the following, and then say whether they're acidic, basic, or neutral. So starting off with the first one, hydronium is 2.7 times 10 to the negative 2. We're going to take the negative log of that to find our pH, and that gives us 1.6. The pOH is just simply then 14 minus that. That gives me a pOH of 12.4. So it's pH that we use to determine acidic and basic. So a pH between 0 and 7 is acidic. A pH from 7 to 14 is basic, and then a pH of 7 is neutral. So 1.6 is clearly in the acidic range. So we're going to say this is an acidic solution. All right, given the hydroxide, you could convert hydroxide to hydronium. You could do this times hydronium gives you 1 times 10 to the negative 14. In this situation, I wouldn't do that. I would just simply find the pOH and then find the pH. So pOH is the negative log of hydroxide, so you just got to pay attention to what you're doing, what you have, because the negative log of this will not give me pH. Negative log of hydroxide is going to be pOH. So negative log of this gives me this, 4.7. So the pH is 9.3, which is greater than 7. So my solution is basic. Now we can also go the opposite direction. So determine the hydronium and hydroxide concentrations, then state if it's acidic or basic. And so remember, we just do the exponential. So pH is 1.7, so 10 to the negative 1.7 power gives you 2 times 10 to the negative 2. We can then do the same. We could use the hydronium times hydroxide equals 1 times 10 to the negative 14. You can use that. The numbers are a little bit funkier. Some people struggle with the scientific notation, especially doing it on a calculator. And so you can kind of play with it either way. I like to just find the pOH, just subtract from 14 and then do this again. I find this to be easier. So I get hydroxides of this. Well, that pH was 1.7, so it is acidic. And then same thing with hydroxide. 10 to the negative 3.1 gives me my hydroxide concentration, because that's pOH. Subtract from 14 and use that to find hydronium concentration, and it's basic. And so that's the basics of using pH to find your values, so you can use them in calculations. All right, so pH meter, trying to figure out exact pH is not always super helpful or desired. So a lot of times we use what we call indicators, and they change color when we get to certain pH ranges. So these are your common indicators. The most common one that you will use is this one, phenolphthalein. That whole pH kind of disappears. It's not phenolphthalein, it's just phenolphthalein is how we pronounce it. That pH kind of is silent. And we use it because it's pretty good and it's pretty close right there around 7. And so it's a good one to use for doing acids and bases. specifically when you're adding a base, which we'll get to in the next section. But these all turn different colors depending upon what you're looking at and what pH range you're looking at. And you can find it online as to what, really what the colors look like. Because this says pink for phenolphthalein. It is a very dark magenta at full pink. And then it's colorless. It looks like water. Which brings me to this one of the things. So we would say the color of water is not clear. The color of water is colorless. Clear means you can see through it. Colorless means it has no color. There's a difference between the two. Because you can have something that is opaque, and usually we would say it's white if it's colorless, but we can have opaque versus clear, and then we can have colorless versus colored. And so that's a little distinction that is important within chemistry and science and just being good at describing things. So that's pH and how it works.